Hello everyone. Today we're going to be talking about entropy, and so I thought, who better to help me explain a little bit of chaos than my cat Ruby, who loves to cause it. So I'll let you do it. She might be making cameo appearances here and there throughout this video, but we will persevere on. So, for our question, this is going to be question 2. We're going to be calculating the delta S naught of a couple of reactions. So our delta S naught is our change in our standard entropy. So we're going to see how entropy is changing as we go through this reaction. We're going to try and see if our sign that we get at the end makes sense. All right, so let's hop into it. So we have our first reaction. So we got AB2 gas plus 2 moles of B2 gas is going to AB6 gas. So luckily, scientists have been doing this for a very long time. Look over my problem here. Scientists have been doing this for a very long time, and we have lovely tabulated values from an entropy table that we can get for each of these species. And so if we take these values, we can use them to find our delta S naught. So let's do that. So in order to get our delta S naught, we need to use a handy little formula. Our handy formula is delta S naught is equal to the sum, so we get to use a cool sum, of the number of moles of products times the normal entropy values of our products. There we go, I can spell, promise. Minus the sum of the number of moles of our reactants times our standard entropy value for our reactants. Okay? So this is our overall formula. You can find this in your white pages if you guys have your modules. And if you don't, you should be able to find them online. I think Miss Dusty shared that with you. If not, just talk to your workshop leader. All right, so we have this. So let's plug in the values that we have. So let's start off. We have our products. We're going to go over to our right side of our arrow. And we're going to put in 175.7 joules Kelvin mole. Now, how many moles do we have of our AB6 over here? That's right, just one. We have an imaginary little ghost 1 in front of here. Same thing over here, imaginary little ghost 1. I see that whenever I look at this. I don't just see a blank space. I see imaginary ghost 1 there. I'm not taking drugs. I see it. Okay, so we gotta see it now. So we'll put it over here. And what that means is that we have 1 mole of our product. So we'll have 1 mole times our S value for this. Okay, so that's all our products that we have. So let's do our reactants now. So we're going to say minus, put in the parentheses. Remember, parentheses are our friends. You never get in trouble for using too many parentheses. So let's use our reactants now. So we have 1 mole of our AB2, so we're going to say 1. Put our 1 coefficient out in front. Remember, we have little moles there next to that, moles. And we're going to put in our standard entropy value for this, which is 95.4 joules per Kelvin mole. And now since we're summing this between our two things, we got to add it. So we're going to add plus our other reactant, which is our 2B. So we have 2 moles. I'll write it down here. We have 2 moles of our B2 gas times its standard entropy, which is 53.6 joules Kelvin mole. Now, if you'll notice, make sure I have enough parentheses, if you'll notice, some of our units will cancel out. So our moles here are going to cancel with our moles here. Our moles here are going to cancel with our moles here. And our moles here are going to cancel with our moles here. So what units will that leave us in? That's right, joules over Kelvin. Standard units for our delta S naught. Okay, so when we go through, and we put that in to our calculator, we go through, we get negative 26.9 joules per Kelvin. So let's think about this. Let's make sure we're not charging $15 for a Big Mac here. does this sign make sense? Well, we have a negative delta S. So let's think, what does a negative delta S mean? It means that our standard entropy for this reaction is going down. We're losing our amount of space that we can put this energy, right? We're losing the chaos in our reaction. So let's see if that makes sense. We have 1 mole of gas here, 2 moles of gas here. So on this side total, 3 moles of gas. Lots of room, lots of space, lots of molecules to put all of our energy into. And on this side, we're going to have 1 mole. So if we're going from lots of moles of gas to few moles of gas, we will have a negative delta S value. I'm getting ahead of myself with delta H. No, delta S. Negative delta S value. Okay? So I think that makes sense. Let's try the next one. Let's see if that also makes sense. So, same idea. We're going to use the same formula. This time we have a different product. We have AB4 gas. So we have AB2 plus 1 mole of B2 gas gives us AB4 gas. All right, so let's set it up the same way. So we have our products. Our only product is AB4. So we're going to have 1 mole of AB4, which is 128.9 joules over Kelvin times moles. We're going to subtract that from our 1 mole, remember, ghost 1 in front of all these, our 1 mole of AB2, which is the same thing as up here, 95.4 joules Kelvin mole, excellent, plus, remember we're summing, plus 1 mole of our, let me put it down here, of our B2 gas, which is 53.6. Okay. Joules. Be a good scientist. Use all my units. There we go. All right. So now let's go through. Let's cancel our units. Remember, I always love canceling things out. I feel like I'm cheating. Mole and mole cancels out. Mole and mole cancels out. Mole and mole cancels out. Excellent. So now we are left with a final answer of equals, let me double check my cheat sheet here. Okay, negative 20.1 joules per Kelvin. So let's think, same idea. Are we charging too much for a burger here? We have 2 moles of gas on this side, 1 mole of gas on this side. Are we going from a high mole of gas situation to a low mole of gas situation? I think we are. Awesome. So our sign makes sense. I think that's all we have for this one. We have successfully calculated the delta S naught of these two reactions. All right. Have fun.